Okay, so next we're going to give the very basic definition that probably you already know of the dimension. Dimension of a vector subspace or a vector space is very simply the number of items in any of its spaces. So you will note the way that is written. What does that imply? It implies that any basis should have the same number of items. Any basis of my vector subspace should have the same number of items, right? And that's a question that I will leave open for you to answer. Okay, think about this after the class. Maybe take 2 minutes now to think about that, but after the class, come with a question next lesson if you haven't found the answer. Why do all the bases have the same number of items? Okay, what's happening? What would happen if you had two bases that have different number of items? Okay, so that's one question for you to meditate on. Okay, so this being said, in a vector subspace of dimension n, we have the next property. Any linearly independent family has at most n items. Okay, so the dimension n means that this is the number of items in a basis. Okay, number of items in a basis. That should be n. So what do we have? Any linearly independent family has at most n items. Okay, basis linearly independent and spanning has exactly n. So if you want linear independence, it has at most n items. Well, that's the idea behind the previous question, actually. All right. Any linearly independent family with exactly n items is going to be a basis. All right, and a spanning family has at least n items. All right, you have to be able to create to reach all the items in your vector space with the linear combinations of your family. So you need at least as many items as in a basis. That's the idea. And similarly to what was before, any spanning family with exactly n items is going to be a basis. Okay, right. So find quick arguments for each point. Again, this is the kind of things you can again think about in the coming days. Okay, next is very important, and I think it's a very nice it's some kind of a proof that we're going to do. It's not completely rigorous, although you could really make it very rigorous. All right, we're going to find a new decomposition for our matrix. So I remind you that previously we had done the LU decomposition. Okay, we had decomposed our matrix A if ever A was invertible and without any um, uh, any permutation, and we're going to find another decomposition. Okay, so decompositions are, well, actually I realized that we're going to do quite a few decompositions this year, but it's very important because some have specific applications as the ones we're going to see next week and the week after, and some other ones like this one, CR, standing for column rows, it's a very beautiful way to describe what really is the framework of the action of a matrix. Okay, the LU decomposition. I hope you understood that it had some numerical interest. That would be how computers proceed in order to do some solving. For instance, MATLAB, in order to solve a system, it would do some kind of LU decomposition instead of inverting some matrix. Okay, so CR again standing for column rows. Okay, so that's all linked to the column space because what's the idea? You've got your matrix A that has, well, I'm going to use n rows and p columns. Okay, and so you know that it's going to, so you've got n rows, p columns. You know that now we're going to consider our matrices as mappings, so they will act on something, so on some vectors. In that case, that's going to be, well, a vector in RP, okay, because I must be able to do the multiplication of the p elements of a row times the whole element of my vector, and that is going to give you, and I'm going to have well, n such products, and that's going to give me an item in Rn. Okay, so this is how we see our matrix as acting from Rp to Rn. And the idea is, well, we have already defined the column space. Okay, what was the column space? That was all the linear combinations of the columns. All right, so this is the definitions that that we gave. So you take your matrix, you take your columns, and you're considering the space that you can create using all the linear combinations of our columns. So obviously it's just going to be a linear combination of these items. So it's just going to belong to Rn, right? And so the idea is that, can we reach any items in Rn? Could I solve anything looking like that? Okay, that's a very usual idea, right? So, and if ever I can solve that, can I solve that uniquely, or do I have an infinity of solutions, right? Solving equations, that's just the point of mathematics, right? So that's it. That's the kind of questions we want to answer. So in order to do that, we one way to look at that is to find out what are exactly the set in Rn that I can reach using my matrix, okay? Um, so we're going to see again ideas of subjection, injections, bijections, but maybe slightly simpler and very lightly, at least during that part of the year. Okay, so some names that I had forgotten to give you about the column space of the image, which is actually the name we're going to use in the second part of the year when we talk about, well, the image of a linear map, right? And or so with the notation IM of A, or another word that is synonymous here is the range of A. Okay, so, and these are very natural words when you consider A, your matrix as a function, actually. Okay, you talk about the image of a function, so you can also talk about the image of your matrix, right? So what we want to do is to find bases for the column space of our matrix in order to understand exactly what are the things that are spanned by the columns of our matrix, right? So we're going to create two matrices, okay, denoted C and R. So again, columns and rows. So in C, we will keep the independent columns of our matrix. So we will consider them one by one and only keep the independent one. And if ever you've got a non-linearly independent column, then you just discard it. And in the R matrix, so you will see that it's going to be a row matrix. You keep track of the operations needed to reconstruct the original columns of A. Okay, so what does that mean? Either your corresponding column, either your it's just, well, it corresponds to you have just selected one of these linearly independent column. In that case, it's going to look like, well, here we have two examples, to look like some parts of the identity matrix. Either it's not going to be, well, it's going to depend on previous columns, and in that case, we need to indicate what kind of dependency we have. Okay, so let me just erase those colors so that we can rework on that. Okay, so few implications before we deal with the example. So if all of the columns are linearly independent, then you just keep all of them, and in your R matrix you will just have the identity. Okay, not the interesting one. But well, it's interesting to go through the process, but it's not the most interesting one. The last non-entry 0 for a dependent column will be at most on the row corresponding to the last independent column, because we do that in order. We keep them in order. Well, it's going to be clearer on an example. Next, so that if the column depends on the previous one, the OR matrix will have complete rows of zeros that we will dispose of. Okay, that's fine. Next, how to describe, note that how to describe combinations of columns we multiply on the right. So that's something nice to see. In the previous decomposition, we were dealing with the LU decomposition. Okay, we were multiplying A by those elimination matrices, E1, E2, etc., E3. Okay, and you are doing multiplications on the left, and these had elementary recombinations of rows. Okay, performing the Gauss-Jordan algorithm, and in order to do that, we would multiply on the left by those elementary matrices. And now what we want to do is we want to do elementary operations on the columns. All right, so actually you can give that a try with some examples. If you want to combine columns, you will have to multiply on the right of your matrix. Okay, so we will have, okay, so that will be our matrix A, and that is going to be just our C and R. And if we want to recombine C in order, the columns of C in order to build the columns of A, we will have to multiply C on the right by matrix. Okay, so let's do that example. Right, so we take one example. We've got this matrix A, which has 4 columns, so V1, V2, V3, and V4, and we want to extract the independent columns. And let's take these assumptions. We have, let's say that, well, the first one, as it is alone, all right, it's a family containing, so we're going to build the family that is going to remain linearly independent. Okay, so first we have nothing, then we have the first column. Okay, let's say we have the first column, right? So we put V1 in C. Of course, as it is alone, this is linearly independent. Then we wonder, should we add V2? Okay, so that's the question. According to our assumptions, we said, well, V2 would be equal to negative 3 V1. So no, V2 is collinear to V1. Okay, so I shouldn't add it to the C matrix. Meanwhile, what's happening in the R matrix? Okay, that one tells you, well, we kept the V1. We kept the V1. So I'm reproducing the identity corresponding column. Okay. Next, I said I'm not keeping the V2, but because the V2 has this linear dependency with respect to V1, it's negative 3 times V1. Okay, so maybe you can try to picture what is happening when you want to build items in V2. Okay, what's happening in that multiplication when you want to build that item? You're going to multiply, well, this one is going to be multiplication. So the first one is just going to be multiplication of that first row of my C matrix times this column, right? So that is selecting 3 times my V1 element, okay, and 0 times the one that comes after, right? Next, if I want to build that one, I'm going to take my second row of my C matrix and again multiply it by my corresponding column. So it's going to be negative 3 times my item in the V1 column and 0 times what's happening afterwards. Okay, so if you read again all the descriptions, all the different descriptions of matrix multiplication, that comes obvious that anything that will belong to that column here, okay, is going to be all the rows of C multiplied by this single column here, right? So if I want to take -3 times my first column, I have to put a -3 corresponding to my first column, this one, and 0 afterwards. Okay, so let me erase all these scribbling so that we can go on, right? So we have, I hope that up to now we agree on these two items and on that one. All right. Next, we have in my matrix A, we have V3. V3, we said, is independent. Okay, so I reproduce the next column of the identity matrix that we have, right? So that's going to be 0, 1. And next comes V4, right? And V4 we said is -2V1 minus 2 minus 4. That's I'm going to change that, minus 4V3. And so in that case, we should have 2 for the V1 and -4 for the V3. Okay, so so if you have understood this process, let me give you one challenge. I'm giving you matrix A, which is 1, 2, 3, 4, 5, 6, 3, 3, 3. And the challenge is perform the CR decomposition of my matrix. Okay, so we will answer in the talk chat. See you soon.